Lesson 7-2, solving exponential equations. So we're still on exponential equations. Just a reminder from 7-1, if you see something like y equals x to the power of 3, that's the category polynomial, like this would be a cubic. If you see y equals 3 to the x, this is a completely different class curve. Whenever a mathematician says exponential curve, they're talking about this, where the x is in the exponent. See the variable there. Okay. All right, so one common application is interest, like earning interest or maybe interest on a debt, or you can take out a loan. So what if it compounds? And last section, you guys saw an equation that looks like this. So some amount is equal to some principal, or this might now is a function of time, right? Some principal amount, say you deposit something in the bank, right? Or take out a loan, go the other way. Times, okay, and then one plus the interest rate. So if the interest rate is 5%, this might be like 0.05. So this whole piece right here is 1.05. Okay. Okay. Now that would be at the end of 1 year, but what about like 4, 5, 6, 7, 8 years out? Okay. So uh, T could represent the number of time intervals, and oftentimes it's an annual basis, so like at the end of every year. Okay? But right off the bat here, they're doing they get more in detail, saying, well, what if it doesn't compound at the end of every year? What if it compounds more often, like every month? Well, if it compounds every month, you might think, maybe this interest rate doesn't apply every single month. But hey, what if I divide this by 12? Because there's 12 months in a year. But then the time I would have to multiply by 12 because there's 12 months in a year, right? So there's 12 of those increments and the larger increment. Right? So that might be something kind of like this. So maybe the amount that you have if you're accumulating interest as a function of time be the principal times, right? And then one plus, right? Now, this is if it's compounding annually. So say annually, compounding, pounding, compounding annually. Okay. But what if it's compounding monthly? Okay. Well, I'm going to take whatever that interest rate is, say if it was 5% or whatever, and divide it by 12. So it'll add a little bit in January, a little bit in February, a little bit in March, and so on. Okay. Okay. And then um, now I've effectively got a much smaller rate here. I can show you what this looks like. Okay, so if it was 5%, the 1 plus r, which would be 1.05, right? That's all it would be originally, right? That's if it compounds annually. But if it compounds every month, it would be 1 plus 0.05 over 12. It would be like, something more like this, 1.004 something, right? So I have to do 12t up here. Okay? Now that's monthly. What if it compounds every in time units, time units. Okay. Well, more generally, this 12 could be like any amount of time. So AT equals P times 1 plus R over N to the NT. So you could do that. Right? What if it compounds every day? N to be 365. Okay. I'll go a little bit extra. I don't think your book gets into this next part, right? But eventually you'll probably see this. Is what if it compounds continuously, like every nanosecond? Okay? And the equation for that actually looks a little different. It looks like this: P times e to the RT. Right, so this is compounds continuously. Right. Now, this character right here, this e, that's a special number in math. And it's right here on your calculator. If you hit second and then ln, or for natural log, but above that says e to the x. So it says e to the something. If you just type 1, like e to the power 1, it'll tell you exactly what e is. Actually, it's an irrational number, so kind of like pi, it goes on forever, non-repeating. It's approximately 2.71828, da 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 da, something like that. All right. All right, but I don't think we're going to quite get into that depth yet, but look for that in the future. All right, so let's go solving these. Number one, solve exponential equations algebraically. So first example, yeah, so hold on to the interest idea. We'll get to one of those later. What if we have 4 to the power of 5x plus 1, and that's equal to 64 to the power of 7? Okay. Okay, now if I took this at face value and say, what is 64 to the power of 7? I mean, it's got to be a huge number. It's 64 times 64 times 64. And you're going to multiply it by itself 7 times. Okay? That says 4 point something times 10 to the 12. 10 to the 12, I think it's like a trillion, isn't it? So it's like 4 trillion. Okay, so something crazy big. Okay. But maybe you don't really have to do that. Okay. Uh, now, what we're really trying to solve for is x. So can you think of a creative way to solve for x? Now, x is in the exponent. So, well, if we were a few weeks from now, like in module 8, your book finally gets to what's called logarithms, which is more systematic way to solve for anything that's stuck in an exponent, just like this is. Right? But just for this module, while we're still in module 7, your book wants you to use a little bit different creative way. So compare these bases, 4 and 64. Hey, 64 is related to 4. 64 is 4 to some power, isn't it? Like 4 times 4 is 16. 16 times 4 is 64. So this right here, I know that 64 itself is 4 times 4 times 4. So I'm thinking about this. Just my little thought cloud. Hey, I can substitute that right there. And then I have bases that look the same. 4 to the 5x plus 1, we're still solving for x, okay, equals, and instead of 64, I'm going to say 4 to the power of 3. Now it's still raised to the power of 7 here, so it's like that. Okay. And now that these bases match, we can actually solve this without ever getting into logarithms, which we will eventually in this class, but not for at least a week or two. Okay. But in time, because here, clean this up one. So 4 to the 5x plus 1 equals, right? Well, if you have a power to power, you guys remember that rule? You just multiply the powers, so this would be 21, wouldn't it? So 4 to the power of 5x plus 1 equals 4 to the power of 21. Okay. Well, now that the bases are the same, hey, I think this power has to match this power. They have to be the same. You gotta be the same, right? So I can just say that's true. So 5x plus 1 equals 21. It's gotta be, right? And now I can just use my regular algebra rules. Right, so subtract 1 from both sides. So 5x equals 20. Right, divide both sides by 5. Right, and then got x is equal to 4. Right, so that's got to be the answer. Make sure that's what the book got. Okay, well, they didn't quite finish it, but it's probably what they got. Right, we can check it anyway. I can take this 4, plug it back into the original statement up here. Remember over here I got 4 trillion and something. Let's see if I get 4 trillion by plugging this into this. Let's see. Okay, so 4 to the power of 5 times 4 plus 1. Do I get 4 trillion? Yeah, it totally is. Same number as we got by doing 64 to the 7. It's the same thing. So we are good. All right, let's keep chugging along then. Say solve exponential equation by graphing. Ooh, we got one of these story equations. All right, since it began in 1966, the extremely high viewership of the Super Bowl has led companies to pay millions of dollars to advertise for just 30 seconds. The average cost of a 30-second ad during the Super Bowl can be approximately modeled by an exponential function. Where the initial cost was $58,000, that was it. Okay, so context here. If you went back to 1966 and you want to advertise for 30 seconds during the Super Bowl, the cost would be 58,000 to do that. Okay. But that average cost is increasing 9.9% per year. The Super Bowl runs every year. So what's an exponential equation that could represent this situation? Right? And there's eventually part B we're headed towards, which is, hey, what year would it have been that the cost to run that would have broken $1 million? Ooh. And it says solved by graphing, but let's set up an equation first, right? And then I'll go over to Desmos and just plug it in. Okay, do that. Okay, so and I'll use that model. So some amount is equal to some principal amount, or I'll say A naught, right, times 1 plus the rate to the times past, right? Now, let's say this is annualized, so this kind of goes back to 7.1, this model I'm working off right here. So that, right, so the amount that would cost after some number of years that have passed is equal to, okay, so here it goes. Now I want to plug in $58,000 right here. Now, what your book is recommending to do is to put this in terms of millions. So in terms of millions, 58,000 is 0.058 million. You say almost 6% of a million, right? By the way, they do have a little typo right here. Yeah, they missed a zero here. Little thing there. So in terms of millions, this would be 0.058. But in terms of straight dollars, better, let's put 58,000. So just different perspectives. Like what unit are you using? I'm using units of dollars. Your book went with millions of dollars. Get the same result. Right, and then 1 plus the rate of growth. Now the rate of growth is 9.9%. So 9.9%. Remember, that's the same thing as 9.9 over 100. Or I could roll the decimal back twice, 0.099, right? Okay, so think about this. Okay, that's what takes the place of this R for growth rate. Okay, so 0.099. There you go. Okay. And yeah, I think that looks like a pretty good model right there. Okay. Now let's go over to Desmos, plug that in. Let's see, can I here shuffle this up a little bit? I think I can put this all on the same screen here. All right, let's try that out. Graphing calculator. Okay, so I'll do, I wonder if it takes A of t, if I can do that. Probably so. All right, so 58,000 multiplied by at 1.099 to the power of t. All right, did not, okay, actually, it doesn't like this notation. Maybe I'll do f of t. Wait, no, it's kind of like, okay, I'm being silly because they're starting at 58,000, of course. I'm being silly. Let's get back to that. It doesn't care about that. All right. What I really need to do is to truncate this y-axis. That's what I need to do. So it starts at 58,000. So I can go to this wrench, go to my y-axis. Let's see. Maybe I can go by, oh, here we go, step. Let's go 100,000 at a time. Let's see if that takes care of it. Oink. All right, so here's what I did. I changed the x-axis from like -5 to 50. I zoomed around a little bit. I changed the y-axis from about 0 to 1.8 million or something like that. All right, shift around a little bit. Right. Creates a much nicer looking graph. Okay. Now everything fits right there. Right. So remember, 1966 is like year zero. So this should be 58,000 right here. Right. Yeah, just like this shows. Right. Right. And then where's it $1 million? Okay, $1 million I see is right here. That looks approximately 30 years out. So maybe 1996 or so. Now I could do this. I could say, let's say y equals 10 to the sixth, that's a million, isn't it? Yeah, here you go, like that. And see where they intersect. Ah, there it is. 30 point something years. So maybe 30 years after, like 1996, it's just a little bit less than $1 million. But maybe the following year, 1997, now we've broken $1 million per 30-second ad. There you go. So that's it. So the late 90s, we're finally hitting $1 million ads for the Super Bowl, according to this expression. Right. Okay. And it tells you how to graph it, but we just did all that. That's exactly what we just did. Right. We framed it, the whole thing. Yeah. All good. Compound interest formula. Here we go. Here's what I was talking about with the compound interest earlier. Right here. So just to remind you guys, right, here's just compounds every time and over like every year. It's real simple. Right. But what if you take that rate and break it into like 12 months or something, right? Oh, you know what I not meant to mention for something like this too is sometimes if you say like reading the news and they say like, oh, there was 5% inflation this month. It's not that there was 5% inflation like strictly within the month of August or whatever, right? It's that if you annualized it, it would eventually come out to 5% for the entire year, right? So if you ever read something like that in the paper or something like that, right? Okay, or in increments or eventually continuously, which we're working towards. But let's play off this one. I think is going to be this next setup right here, example 3. Luciana deposits 1,700 into a savings account that pays 1.8% annual interest. Ooh, compounded monthly. Ooh, yeah. So we're doing increments of like 1/12 of a year. Right? Right, what will be the balance after 5 years? 5 years. Right? So we say the amount as a function of time could be, okay, well, I'm using this. So the principal times 1 plus the interest rate divided by well, let's do 12 months, what we're going to do. Okay. And then 12 months in a year times the number of years that pass. So t is still the number of years. Right? Alternatively, you could just, instead of 5 years, you could say, oh, 60 months. Right? So that's kind of an alternate way to do it. Okay? But let's do this here. So I'm going $1,700. That's that principal right there. Just put in $1,700. Okay. 1 plus, now there's a 1.8% rate, so it's 0.018 as a decimal, right? That turns into a decimal. But compounded monthly. So we're going to make that interest rate even smaller, but it's per month. So actually it works out to even better than 1.8% by the end of the year. Right? Right. And then we're doing 12 months in a year, and then we're doing 5 years. All right, so all right, all I gotta do is just plug this straight in the calculator. Okay, and it will tell me how much. Okay. So let's see, what's $1,700? Take $1,700, okay? Multiply by 1 plus, and then here, open an parenthesis here, why not? 0.018 over 12, close, close, now I closed up to here, and then power of, and then new parenthesis, 12 times 5, or 60 if you like, 60 more. Okay. All right, I'm looking at, so dollars, $1,859.97. Okay. Okay. Side thought here is what if this had not been compounding monthly? What would the difference be? Okay. So this is if compounded monthly. Okay, let me little space. I'm going to do a little math here. I'll say if compounded annually. Okay. I wonder what it'd be. Okay. So that would be $1,700, and then just 1 plus 0.018 to the power of 5 is 5 years. Right. Let's see what that would be. 1,700, 1.018 to the 5. Right. That comes out to, yeah, $1,858.61. Right. Right. You guys see how by compounding monthly, she makes a little bit more than if they'd just been compounded at the end of the year, right? It's not that big a difference, but it is a little bit more. I'm going to throw in one more. What if compounded, bounded continuously, right? Like every nanosecond, you're doing a constant compounding process. Okay. Now, this is the one that we haven't quite got to yet in your book, but we'll probably eventually see. $1,700, and then that special E character on your calculator, 2.718, to the power of 0.018, and then 5 for 5 years. Okay, let's see what this will come out to. I bet this one comes out to even more than this monthly compounding, but probably not a lot more. But let's say 1,700 e to the power of 0.018 by 5. Um, that's 1860.10. Yeah. Okay. Yeah. Yeah. So it's a tiny bit more, but not hugely significant. But so. All right. All right. Let's jump into the book puzzles. Chapter puzzles. So number one, solve each equation. I got 25 to the 2x plus 3 equals 25 to the 5x minus 9. Oh, well, look at that. It got a common base. So 25 to the something equals 25 to the something else. I think that these exponents have to be the same. Right? They also have to match. Right? So the 2x plus 3 has to be 5x minus 9. It has to be the same thing. Right? Because 25 to that power, 25 to that power. Right, so now we can just use regular algebra rules to solve for x. So maybe we get all the x's on one side. I'll subtract off 2x from both sides. Here, I'll add 9 to both sides while I'm at it. Okay. Add everything up, see what we get. So on this side, I got 12, because 3 and 9 is 12. Okay. Over here, I got 3x. Okay. Divide both sides by coefficient 3. 4 is equal to x. Okay. So for that original statement to be true, x has to be equal to 4. That's it. Of course, you could try that. You could plug in 4 there and get the same number on both sides. All right, next one, number 6. We got 125 to the power of 3x minus 4 is equal to 25 to the 4x plus 2. Okay. So not exactly the same base, but it looks like they have something in common. Because I know 25 is 5 squared. I know 125 is 5 to the power of 3. So I can get them to have the same base, which would be 5. Let's see how I can do that. So I know 125 is equal to 5 to the 3. I know that 25 is 5 squared. So I'm thinking about this, thinking about this. Like, hey, I got a little substitution here. So instead of 125, I'll call it 5 to the 3. That's raised to the 3x minus 4. Okay. And over here, I got 5 squared, and that's raised to the 4 plus 2. Okay. Right. Now when you have powers raised to powers, well, you just multiply the powers. So it's 5 to the, do I want to distribute this? Well, let's go ahead and do it. 3 times 3x is 9x. 3 times 4 is 12. We're subtracting that. So look at that. Over here, it says, let's see, 2, that's 5 to the power of, that's 8x plus 4, I think, right? Is that it? I think that's right. Okay. Right. Ah, now this looks a lot like the last one. You have the common base raised to different looking powers. So actually, these powers must be the same as each other. Okay. So this and this must be the same. The same thing. Right, so let's do it. So 9x minus 12 equals 8x plus 4. Okay. So let's see, subtract 8x from both sides. While I'm at it, I'll go ahead and add 12 to both sides. These separate steps if you like. Okay, so, okay, over here I just get x. So we're about to get the answer, whatever this is. And over here, it's 16. Okay, that's it. Whole thing. Okay. Here, I'll check this real fast. Let's take 16, plug it back into the original statement up here. Here, I'll switch the paper so this all fits on the screen here. And then just plug this in the calculator. All right, so here's where we started, here's where we ended. Got a little skip right there. So taking 125 to the power of 3 times 16 minus 4. Let's see, what is this? Oh boy, 1.8 times 10 to the 92. Uh, okay. I want to say in physics that might approximate the number of hydrogen atoms in the observable universe, but okay, so 10 to the 92. Is this side also 10 to the 92? Let's find out. 25 to the power of 4 times 16 plus 2 is, yeah, it's the exact same number, 10 to the 92. All right. Right, next, number 7, interest. Bianca invests $5,000 into an account that pays 5% annual interest. Write a function that represents the amount in your account after X years. How many years will it take to get to 25,000? Round to the nearest tenth if necessary. Okay. All right, so number 7. Okay. So the amount after some time is equal to the principal times 1 plus. Now, it looks like here we're just compounding at the end of every year. So I'll just go with the straightforward one. 1 plus the interest rate to the number of years that pass like that. So, yeah. So the amount after some time is equal to have $5,000 principal right there multiplied by now 5% interest rate. So R is 0.05, and we're doing 1 plus that. So it comes out to 1.05. Okay, and that's raised to the power of however much time has passed, just like that. Um, okay. Well, they wanted this to be Y and the time to be X, but otherwise that's the correct model. Okay, so you just use that. Right? You type that into Desmos and we show you exactly what the curve looks like, the exponential curve. Okay, how much time to get to 25,000? Like how many years to get to $25,000? Well, if you let this be $25,000, can you solve for t? You see round to the nearest 10. Okay, here's where there's a few ways to solve this. Right? One is that I could go through my algebra rules until I run to a dead end, and I could pull a calculator and start plugging in a bunch of years down to the nearest tenth. Right? So you could do trial and error, guess and check until it gets pretty close. Right? The proper way to solve this is with logarithms, which we haven't gotten to yet, but that's module 8. Right? I can also use Desmos. Desmos. Let me just go ahead and plug this right into Desmos. That right there. All right. Try this out. I oughta let's see if I can refresh this. Oops. Hang on. Every time I type on this keyboard, lose connection there. All right. All right, so let's go. The amount as a function, whoops, as a function of time is equal to $5,000 multiplied by 1.05 to the power of t time has passed. Right? All right, so I'm gonna go to this wrench. I want to scale my y-axis let's say from, okay, -9 looks good. Well, at least 5,000. Let's go 12,000. That might be reasonable. Okay. And then the x-axis, how many years? Let's go from zero. Whoops, that's not right. Let's go from time -1 to about about 30. Let's go 30 years out. Let's see if it fits in there somewhere. Okay. Uh, okay, and of course I can still scroll my mouse wheel after that. So as long as I get it pretty close, right? There's your curve. What are we looking for? Okay, we want to go to $25,000. Oh, of course I want to scale this up to 25,000. All right, so let's make a new equation here. I'll go A equals 25,000. Nope, didn't like that. Let's go as a function of time. There we go. Right. Right. And then wherever these cross, bam, that's your answer. So to get to $25,000, it takes 32.99 years. Let's just call it 33 years, right? Yeah, 33 years. That's the answer. It takes 33 years, even to the nearest tenth. The answer would be 33 years. 33 years is the answer. So dot, 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 t equals 33 years. Right. If you're doing the guess and check method, then you could just sit here and plug in a bunch of stuff for t. So 5,000 times 1.05 to the power of 30.0. If you're doing it at 10th of the time, it should be pretty dang close to 25,000. Let's see if it is. 1.5, whoops, 33 years. There we go. Yeah, 25,000 and change. Right, number 10, battery life. The battery life of a certain cell phone starts at 8 hours. The battery life decreases at an annual rate of 30%. Yeah, I remember just a couple decades ago, back when I was in college, I had to buy a new battery for my cell phone every few months. But yeah, nowadays they last for years. But yeah, they do have a lifespan of this. Right? It actually follows well, according to your book here, an exponential decay curve. If you remember this one from lesson 7.1, I pulled this one out. Now this is showing radiometric dating, like radiocarbon dating, for example, right? But that's the same mathematical curve. So maybe your battery life starts like, oh yeah, I can charge up in the morning, it lasts for 8 hours, right? But then after, some amount of time, it's like, I charge it up in the morning, but it only lasts like 3 or 4 hours, right? And it gets less and less and less, right? And so that's what we're looking at. Okay. So how can we put this into a model, right? And then eventually there's a follow-up question. After how many years does the battery life only go down to 2 hours? Right, so eventually, so in time. So we can still use this exponential curve. The amount is equal to the initial amount times 1 plus the rate to the amount of time. Okay, so that's our basic model. Now we're starting off with an 8-hour life. So that's goes right there. Okay. Okay. And this could be like the lifetime or the number of hours it'll last after so many years. So t is the number of years. Okay. Uh, Now it's losing 30% of its battery life every year. Okay. So this r is like negative 0.30. Isn't that negative 30%? Okay. Now you put this all together, 1 plus negative 0.30, it comes out as 0.70, right, in t. And that right there is the model. So here, to show you guys how this is working, I'll make a little table. We haven't done a table yet today. Okay. So, and of course you could make a graph. The graph would look a lot like this. It'd be the same shape as this. Okay. But what does the table look like? So I'll say t, which is the number of years past, right? And well, a is a function of t. Okay, so like how long will the battery life last? Okay. Let's say you buy a brand new battery for your phone, so it's been around for like 0 years. You pop it in, you charge it for the first time. Okay. And then 1 year later, 2 years later, three, we'll just go by whole numbers. Okay. I wonder how it's going to be doing after 5 years. Let's do that. Okay. Right, so just take 8 times 0.7 to the power of 0. And oh, look at that. By fresh out of the pack, it will last 8 hours. So this is an hours, 8 hours. How about after 1 year? After 1 year, it's down to 5.6 hours. So you charge it up, lasts for 5.6 hours. Yeah, that's a 30% decrease. Said 30% decrease, didn't it? How about after 2 years? Well, that's like 70% of 70%. Now we're down to 3.92 hours. Okay. How about after 3 years? I'm going to round here. 2.7 hours. How about 4 years? About 1.9 hours. How about 5 years? All right, now we're down to about 1.3 hours. Okay. Now your book asks how long would it take to get to, I think 2 hours. There it is. Yeah, 2 hours. 2 hours. So, okay, round to the nearest tenth. We can just use this table method. I used a graph method earlier for a different example. Okay. I do see that 4 years is pretty close, but we've overshot it a little bit. So it's somewhere between 3 and 4. Let's try 3.8 and 3.9 and see what happens with those. Okay, look for the nearest tenth, right? Let's do 3.8. This is 2.06 hours. How about 3.9? This is, look at that, 1.99 hours. Right, I think that's the winner right there. Right. So after about 3.9 years, now your phone can only hold its charge for about 2 hours. Or that particular battery, I should say. All right. Number 11, banking. Uh, Seal bond deposits $1,200 into a savings account that pays 5.2% annual interest compounded monthly. Ooh, it's compounding. What will be the balance after 4 years, round to the nearest cent? Okay. Okay, so we're playing off this a equals a naught times 1 plus r to the t, but we're compounding monthly. So let's get a little more specific, right, which is like 1 plus, and then whatever the interest rate is, that's really an annualized interest rate. We're going to divide that into, well, 12 months. I'll say n for number of months, which will be 12, and then number of months in a year times number of years. That can tell us how much is accumulated. Blah, 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 blah. All right. All right, so $1,200 is deposited, so that goes right here. So the amount after some time is equal to, we're starting off with $1,200. $1,200 in the bank. Cha-ching. And then 1 plus, now it's 5.2%, so that's 0.052 as a decimal. But then let's divide that by 12. Notice I'm only dividing the interest rate itself by 12. I'm not including the 1. Right, okay. Right. So we're taking the interest rate, we're dividing it to like 12 parts, right? And then 1 plus that. So the interest rate is really, okay, 1 plus 0.052 over 12, right? All right. It's really like a 0.43% interest rate per month. Right? So then we're doing 12 months in a year times the number of years. So T is still the number of years. Okay, so this should be the model. What else do they want? What will be the balance after 4 years? Round to the nearest cent. Okay, so look for A of 4. So after 4 years have passed, let's take $1,200 multiplied by, I'll just write this 0.052 on 12, and then 12 times 4. So 48 months, you could think of it that way. It have passed. Let's see what the calculator says. 1,200, 1 plus 0.052 on 12, all raised to the 12 times 4 is 48. Okay. I'm looking at $1,476.79. Cha-ching. Yeah. All right, pretty good. Pretty good. Okay. Now you might say, okay, let's earn 270 something dollars, just from interest. That's pretty good, right? Let me remind you guys from yesterday is what if you hadn't left this in this account for 4 years? What if you left this in an account for like 20 years? Like 20 years. Hey, it's the same $1,200 deposit. After 20 years, you'd be up to over $3,000, like almost tripled the amount of money. Right? Yeah. Hey, that's a good rule of thumb, right? If you're earning over 5% interest, you're leaving it for 20 years, you will have almost tripled whatever your initial deposit is. Ignoring inflation, I think maybe that's a real interest rate. And so I saw more of these. Okay, so got some pure math looking ones queued up here. 22. 1 over 5. Oh, fraction. 1 over 5 to the power of x minus 5 is equal to 25 to the power of 3x plus 2. Okay. Okay, so we're solving for x. Now I see x shows up in two places. there and there, right? And they're both in the exponent. Right? Again, a very mathematical proper way, like procedural way to do this is to bring in logarithms, which we haven't gotten to yet. Right? But for now, we're going to use this method of we're looking at these bases and say, hey, 1 over 5 and 25, those have something in common. 1 over 5, that's like 5 to the negative 1. And 25, well, that's like 5 squared. So they both have something to do with 5 as a base. Oh, okay, well, I can take advantage of that. Just plug this in. So instead of 1 over 5, I'll just say 5 to the negative 1. That's all raised to the x minus 5. And on this side, it's 5 squared. And that's all raised to the 3x plus 2. Right? Right. Ah, okay. Now I remember what now. Right? This is a lot like some that we did earlier. Right? Just that this number is negative. That's the only thing that's kind of new. Right. So you just distribute right here. Power to power, you multiply it. That's 5 to the power of negative x plus 5. And reverse the signs. Equals, and then 5 to the power of, see, that'd be 6x and 4. Okay. 5 to the something equals 5 to the something else. Well, these must actually be the same, just like before. See before. So now we can solve this with regular algebra. Okay. So negative x plus 5 must be the same thing as 6x plus 4. Let's add x to both sides. I'll subtract 4 from both sides. Kind of two steps in one there. And so on this side, I end up with 1. On this side, I end up with 7x. Right. Divide both sides by 7. Therefore, x is equal to 1 over 7. Looks good. Yeah. Bam, bam. Number 27. So right here. Oh, we got 81 to the power of a plus 2 equals 3 to the power of 3a plus 1. Okay. Well, we must be solving for a in this case. A. Okay. And 3 versus 81. Well, I know that 81 is 3 times 3 times 3, which is like 3 to the power of 3. So I'm thinking about this. Okay, all right, I can substitute that right there. So 3 to the power of 3, and that's to the power of a plus 2, is equal to 3 to the 3a plus 1, like that. Right? Okay. Oops. Okay. Next step, distribute those 3, right? Because power to a power I can multiply. So 3 to the power of 3a plus 6 equals 3 to the 3a plus 1, like that. Okay. Right, so 3 to the power of this equals 3 to the power of that. So this and this must be the same. Right? Bring that down. 3a plus 6 equals 3a plus 1. Oh boy. You guys see we're going to run into a little issue here. Like if I subtract 3a from both sides, can't really do that. Minus 3a, minus 3a. Okay. You guys see I end up with 6 equals 1. Okay. Which is false. Okay. Which means there's going to be no solution. Which means there's nothing you could ever plug in for a in the original statement to ever make that true. The answer is no solution. Okay. Let me show you guys what this looks like graphically. Graphically, if I turn these each graphs, say y equals this and y equals this, then those two graphs would just never cross each other. So let me pull that up on Desmos. Here, clear all this out. Here, let's start over. Yeah, clear all that. Okay. So if I say y equals, see, it was 81 to the power of, it says a plus 2. I'll just call it x plus 2. Right. Right. And then down here I have y equals, this was 3 to the power of 3x plus 1. Okay. Now, according to my solution that I got, it said that there's no solution, that these two graphs would just never cross. Yeah, it looks like they, in fact, never cross. Right? Um, you know what? They're actually, I think these are the same curve, just translated. It's like if you take one curve and just shift it to the left. Yeah, that's what that is, isn't it? Yeah. Okay. Of course, that's why they would never cross. All right. So there's a little alternate way of looking at that. Boom, boom. All right. What's next here? 34. 34. We got 1 over 3 to the power of m equals 27 to the power of m plus 2. Okay. Okay. I guess we're solving for m. Okay. Well, 1/3 and 27 do have a common base because 1/3 is the same thing as 3 to the negative 1. And 27 is the same thing as 3 times 3 times 3, or 3 to the third. Right? So I can substitute. So let's do 3 to the negative 1 in place of a third, and that's to the power of n. And over here, I'll do 3 to the 3, and that's raised to the n plus 2. That. Okay. Now, just like before, power to power, multiply. So 3 to the negative m equals 3 to the 3m plus 6. Okay. Okay. And now you have a common base, which is 3 in this case. So these powers must be the same as each other. This and this are the same. So negative m must be equal to 3m plus 6. Okay. So let's do plus m on both sides. I'll do minus 6 on both sides. Okay, so that gives me negative 6 equals 4m. Divide both sides by 4 over 4 over 4. I think m has to be, that reduces to negative 1.5. Negative 3/2, doesn't it? I think it's got to be that. I'm going to check my work on this. See a calculator. So let's go 1 over 3. I'm going back to the original statement. Let me do what I did before. Or actually, you know what? Maybe I can just turn this way. Yeah, here we go. Right. So I'm taking this answer right here. I'm plugging it back into the m's for the original statement. I'm going to see, does the left side match the right side? So I do 1/3 to the power of negative 1.5. And from that, I get 5.196, something, something, something. So I'll jot that down, 5.196. All right, hold on to that. Okay. Is that the same as if I plug this in into here? 27 to the power of negative 1.5 plus 2. It's the same thing. Bing! Oh, yeah, same thing. Oh, good. Keep going. 52, economics. The Jones Corporation estimates that its annual profit could be modeled by this expression, and Davis profit could be modeled by this expression. For both equations, profit is given in millions of dollars, and T is the number of years since 2015, which would be the base year. All right, so we're looking at, here I'll call it Jones as a function of time is $10 million times 0.99 to the T. And Davis as a function of time, these are profits in millions of dollars, so $8 million times 1.01 to the power of T, like that. Okay. All right, so it looks like in the base year of 2015, so time is equal to 0, all this goes away. Jones is worth 10 million and Davis is worth 8 million. Okay, so Jones is worth a little bit more. But something funny about these growth rates. Is this the okay, so for profit rate, okay? It's 0.99. That's a tiny bit less than 1. That means the more time has passed, Jones's profit is actually shrinking, right? Like if you run 1 year, it's actually less than $10 million, right? And the Davis profit, ooh, look at this growth rate. It's like a growth rate of 1%, you could call it. Well, it is growing. So the next year would be a little more than 8 million. I bet if you ran enough time, at some point, these curves would cross and Davis would eventually become more profitable than Jones, because Jones looks like is getting less profitable and Davis is getting more profitable, right? You know, it's a tiny difference in these rates, right? And you can probably imagine that behind the scenes, you can make some managerial decision that could, tip it from being a shrinking company like Jones to a growing company like Davis, or vice versa. Okay? You know what this kind of reminds me of too? You guys remember a few years ago when COVID was spreading around, talking about something called, I think called an R value or something like this. It's like how likely are you to spread COVID to another person? Or you could apply it to anything, cold, the flu, whatever. Okay? And if this rate was less than 1, then it would be a virus that would eventually shrink out. Like if you only were like 99% likely to give it to somebody, eventually it's going to run to a dead end, right? But if this number is greater than 1, like if you're likely to pass it to somebody else and maybe someone else besides that, right? So maybe a friend and possibly somebody else on top of that, right? It's eventually going to be passed on to like the entire world, right? Which is kind of what happened, right? So there you go. But what is your book point out of this? Find the company's estimated profit in 2015 and 2025 to the nearest dollar. Right. Well, 2015 I know because you just plug in zero, $10 million, $8 million. Okay. So J of 0 is 10. Well, I'll write the word million dollars. Right. And Davis at time 0, so your 2015 is $8 million. Right. Now, what about Jones after 10 years? What about Davis after 10 years? Let's see. Now, I just made the claim that Jones has to be shrinking. So let's see if that's what the calculator math says. Take 10 to stand for 10 billion, $10 million times 0.99 to the power of, well, let's go 10 years. T could be years. Okay. Okay. Now this company is only worth 9.04 million, or profit. Okay, so profit 9.04 million. Okay. What about the Davis profit? Now, Davis started out with only $8 million dollars profit, but it is growing every year. Let's run 10 years in the future. Ooh, look at here. 8.84 it rounds to $1 million, right? Okay, so even after 10 years, looks like Jones is still worth or profiting a little bit more than Davis is, but you see that's not sustainable, right? So I bet if another 10 years that would have reversed by then, right? Because you're getting pretty close even after 10 years. Which company would you prefer to own stock? Explain your reasoning. Well, I think stock price. I mean, if you're gonna maybe invest going forward and say which can be more profitable, or if you're looking to trade the stock for more value eventually in the future, I would go with a company whose profit is growing, not the company whose profit is shrinking. Even though Jones starts with the larger nominal profit, 8 million is more than, or sorry, 10 million is more than 8 million. Right? The growth rates change the equation down the line. So, 10, 15, 20 years in the future, right? I'd be more interested in a company that actually has growth behind it. Right? Oh, I got one more for you guys. One more. Take a look here. 62. If you were given the initial and final amounts of a radioactive substance and the amount of time passes, how could you determine the rate at which it was increasing or decreasing and write an equation from this? Okay. That gets to what this is. Now, here I'm showing continuous compounding, like PE to the RT. Sometimes you see it. Okay? But you can write it annualized. I mean, there's a way to do that too. Okay. So how could you do that, like in principle? Big picture idea here. You have to apply a little bit of creativity. Well, I can work from this model. The amount after some time is equal to the initial amount times 1 plus the rate to the number of years that have passed, right? So this would be an annualized rate, and maybe T could be the number of years, right? Or since we're talking about something radioactive, some compounds are radioactive in terms of years, like carbon 14 is like 5,000 and something years. That would be its half-life, right? Yeah, a lot of atoms are radioactive, have half-lives like a fraction of a second. So maybe time could be in seconds even, or something like that. Anyway, you have to pick a scale for this time though. All right, so right, how would you determine the rate the amount is increasing or decreasing? Right. Well, again, a common way to do this is what's called half-life. See where I have a subscript on this T, it says T sub 1/2, right? That's called half-life, right? So how much time does it take to decay to half of its original value? Right. So if there was some original value A naught, right? How much time does it take to get down to half of that? Right. And whatever time that is, right? So whatever the half-life is, in this case for carbon 14, it would be 5,000 something years, right? If you let another interval of half-life go by to like twice that time, now you're half of that half, right? So half of that, now you're down to a quarter of the original amount. Let another half-life go by, now you're down to an eighth. You said you start off with 100%, get 1/2, 1/4, 1/8. I bet for another half-life it'd be down to 1/16, right? And this might be accurate, thousands of years out, maybe like 30, 40, 50,000 years or something. All right. So I think I'm going to write down the word half life. Okay. So maybe it's something like that. Like whatever the initial amount is, you can say you have this radioactive substance, say in the lab, and you just wait for it to decay to half of that original value, right? If you have enough time, maybe not carbon 14 as an example, because you'd be waiting over 5,000 years, right? But maybe a different radioactive substance, right? Something like that. And then, or if it was carbon 14, maybe you don't care about half necessarily, but you could go with a different model. Right. And then 1 plus, looks like we're solving for the rate. Right. And then, okay, solve for R, right? And let whatever interval of time you want go by. So I might set this to like 1 year, for example, right? Or however much, actually, no, I'm getting silly about that. Right? So this would be represent the half-life. Right, and we could determine that too. Okay. Okay. Now, whatever you start with, say if you started with like 10 grams of substance, so you end up with half of 10 is 5. Okay. Okay. This ratio will always be the same if you lock it into that. Okay. So I have half the amount after, I'm gonna just let this naturally run in my laboratory, right? I have like some equipment that I can use to detect, right, how much I have. Okay. And I want to solve for this R right here. Okay. And I'll naturally let the time go by. So my laboratory experiment is going to tell me what this is. So this comes from the readings, okay? And this comes from the readings. Okay. Okay. And then I can calculate what this R is. Okay. Now, the proper way to do that, again, would be using logarithms, right? Or you could sit here and guess and check and, tell you get it that way. Okay. Now, this is with it's like an incrementalized way of thinking about this, maybe annualized if this is like if some number of years, if it came out like that. Okay. Again, an even better way to do this is with continuous compounding, and that brings in this E. Okay, so if you went that level of detail, you could say the amount after some time is equal to the initial amount times E to the, I could say negative KT, maybe something like that. Okay. No, I'm including the negative myself because I know this is going to be exponential decay. So don't let that. If I forgot to include the negative, it would naturally come out negative anyway. It's like, oh yeah, that's right. It would have to be. Okay. Okay. And then just like with this other method I did, I could call this 1/2 A naught and this A naught, and then e to the negative k. And this t would become the t 1/2 would become the half-life. Okay, so okay, that happens just like before. E is about 2.71828. It's stored in your calculator. Okay, and then I could solve for k either by guess and check or with logarithms, right, which will be a future topic. All right, so that's about what that looks like right there. And that is module 7.2.